Good morning. Today we represent my college to present a paper detecting hate speech content using embedding models. Please excuse me if my presentation has some noises. On the screen is the outline of my presentation today, including 4 sessions. Firstly, we briefly introduce our study. Secondly, we describe our robot method. Next, we present the experimental setup and results. Finally, we draw a conclusion. Before we discuss the details of this paper, I would like to present some definition of hate speech content. According to the Oxford Dictionary, hate speech is a speech or writing that attacks or threatens a particular group of people, especially on the basis of race, religion, or sexual orientation. We can see that the Cambridge Dictionary also has a similar definition. Although the community already has a definition of what hate speech content is, the process to determine hate speech content is not often straightforward. In this slide and the next few slides, we report some current challenge of hate speech detection. From July to December of 2020, Twitter has removed 3.8 million hate speech tweets on its platform. As mentioned earlier, the process of automatically detecting hate speech content is not often straightforward. For example, as reported by The Verge on October 17, 2021, Facebook AI cannot detect hate speech or violence consistently. A week later, the Washington Post reported that Facebook fails to filter hate speech and fake news in India. In general, hate speech detection can be considered as a text classification task, which is a machine learning technique that assigns a set of predefined categories or labels or class to a given text. In particular, the aim of hate speech detection model is to assign a label, hate speech or not, or a set of labels, for example, hate speech, offensive language, or neutral to a text. Due to the unstructured nature of text data, in this study we propose a knowledge-rich solution to hate speech detection by incorporating hate speech embeddings to generate a better representation of the given text. Previous studies exploit a lot of linguistic features to represent a text, for example, lemmatization and RAM back-of-word, back-of-speech tagging, sentiment lexicon. To overcome the limitation of previous studies, in this study, we employ neural network models to enable our probable model to be able to automatically learn representation of features. On the screen is the overall of our robust model. Given a sequence of words, we first represent each word as a d-dimensional word vector by concatenating word embeddings and high-speed embeddings, and then we feed the word vectors into a neural network model, followed by the submap function to normalize the output to a probability distribution over predicted labels. There are two main steps in our study. The first step is performing high-speed dictionary construction, and the second one is representing an input text. In order to construct the high-speed dictionary, we perform the following procedure. We construct the high-speed dictionary containing on instance label as high-speed or offensive language from popular datasets. Also construct a neutral dictionary to include We also construct a neutral dictionary to include the instance label as neutral. When conducting this procedure, it poses a problem that the high-speed dictionary may contain some irrelevant words. Therefore, to eliminate them, we assume that a word appearing in both dictionaries is not a hate-speech or offensive word. To do that, we employ the NLTK library to compute the similarity between pairs of words and eliminate on pairs whose similarity score are larger than or equal to 0.5. Before employing the high-speed dictionary, we deliver it to annotators. And with the approval rating at 70%, the high-speed dictionary includes 766 terms. In general, the input representation is a concatenation of word embedding and high-speed embedding vectors. Four layers transform a work into a vector representation of the dimensional. For our embedding layer, we employ the work-to-vec model to generate a 300-dimensional work vector for each given work. For high-speed embedding layer, we denote by a Boolean scalar value to indicate whether a given work is a high-speed term or not. Technically, the dimension of the work embedding vector is 300 and high-speed embedding vector is 1. Therefore, the input representation is a concatenation of the true embedding vectors denoted by a matrix I with L rows and 300 columns. After obtaining the input representation, we are now feeding it into three sorts of neural network models, specifically a multilayer perceptual model, CNN model, and BioSTM model. For multilayer perceptual model, first we obtain a vector representation by performing an element-wise summation over the embedding vectors as shown in the equation. The obtained vector is then fed into a multilayer perceptual model consisting of two hidden layers with wrap-out and rectified linear unique activation functions. On the left is the architecture of the CNN model, and on the other side is the architecture of BioSTM model. For CNN model, we set up the filter of the CNN model as an NRAM feature. Given the input I, we define a filter W with H rows and D columns, where D is 301 and H acts as an NRAM feature. The convolution operation of a filter on H consecutive work vectors outputs a scalar value. Therefore, employing M different filters output a vector C with M dimension. In general, given a tag of length L, we obtain L minus H plus 1 vectors after performing the convolution operation over the text. In case of IOSDA model, for each given work, we first compute the hidden state vector from the left to right and right to left directions. We then concatenate the last hidden state vectors of each direction to a vector S with 2k dimensions. We then feed vector S into submap function. In previous section, we described our proposed method and model. Now, in this session, we describe the experimental setup and results. We employ three datasets as shown on the screen. The first two datasets obtained from paper A and B is referenced at the footnote. The last dataset by combining the first two datasets. The details of how we construct the last datasets are presented in the paper. To conduct the experiments, we consider two cases. First, using only word embedding. Second, concatenating word embeddings and high-speed embeddings. For neural network models, we evaluate three sorts of models. In particular, first, a multilayer perceptual models, second, a CNN model, and the final is BioSTM model. In the above table, the experimental results show that the CNN model has achieved the best performance in both two cases, true and false, for all datasets in terms of macro F1 measure. In the below table, for the HASOC 2019 dataset, we can see that the method in SIG outperforms the other ones, since its model is by far larger than our proposed one. For HSOF3, the authors aim to manually consider each linguistic feature. It thus can help the model to be well fit on the dataset. For HS through 2021, the combination of the first and the second dataset significantly enriched the macro F1 score. In summary, we have shown that the combination of word embeddings and high-speed embeddings can produce promising results in comparison with the methods that employ large-scale retrained language models. In the next section, we draw a conclusion for this study. In this paper, we have proposed a high-speed detection model that combines word embeddings and high-speed embeddings. By incorporating the high-speed embeddings, we can generate a better representation of the given text. The experimental results have shown that our robust model achieves promising results even though it is quite simple when compared to the others that employ large-scale retrained language models. And in future work, we plan to expand the high-speed dictionary with more fine-grained labels and assign weights to high-speed terms. And finally, thank you for your listening.